Yeah, so hi everyone. Welcome back from COVID or wherever you were. So I'm just going to be talking a bit about ion chambers and reference dosimetry. I'll talk a bit about the end about some other chambers as well and relative dosimetry, but this is the main focus. So kind of just a quick and easy one. I'll just sit down because I can't find the pointer. So I'll start basically from the beginning. Ionizing radiation ionizes particles in a gas, which separates into positive and negative charges. And so the principle is if we apply an external electric field, we can collect these charges produced by these events. And then you can kind of correlate this to the amount of ionization, which is a way of quantifying the radiation dose. And on average, just a little thing to remember, you get about 30 to 35 electron volts of energy per ion pair. So here we've got an electrometer. So in real life, it'd look something more like this. A little bit more background. Bragg-Gray cavity theory tells us that what I mentioned before, the amount of ionization in the gas-filled cavity is related to the energy absorbed that you would get in the surrounding medium. So we're trying to relate this ionization in our cavity to what we're really interested in, which is the dose to a point in the medium. I won't go too far into the theory of this because it's not that useful practically. It's very important to understand, but we don't really use it in our reference dosimetry directly. So, but basically there's the main Bragg-Gray conditions, which you've probably learned about, is that the cavity should be small enough that it doesn't disturb these electrons, and that the energy deposited here is only deposited by electrons which cross through the cavity. So this looks more like a pharma chamber, so this is more like something we use clinically, and we use it to measure dose. So we're measuring the charge, and then we use a formalism, dosimetry formalism, to convert that charge to the absorbed dose. What we use in Australia mainly is this IAEA TRS 398. And the sort of most basic part of it is that you have a calibration factor to go from your charge to the dose in the reference conditions. So a quick bit about ion chambers. So they're robust, they don't really change, they're well understood. You can position them easily and accurately, especially this kind of pharma chamber, because we can position this pointy end accurately at the surface of the water, which enables us to say, 10 centimeters deep is accurately 10 centimeters deep. Now, a small ion chamber would be great because you'd be measuring like a pinpoint, which is what we really want, but they need to be large enough that you have enough gas for them to be sensitive. So there's kind of a trade-off between the size and the volume averaging. So kind of still in background here, but primary standards. We prescribe dose in gray, which is joules per kilogram, because this basically correlates with patient outcomes. It wasn't always this way, but dose is the quantity that ultimately we're interested in now. So this calibration factor, so how do we actually find it? What are our chambers actually calibrated against? So at the end of the day, somebody needs to determine the dose from its definition, so figure out what's the real joules per kilogram. And these ion chambers that we use clinically aren't actually capable of doing this accurately. So what we end up doing is we have a reference chamber that we send to a primary standards, and then they have a sort of special chamber like this. So this is a graphite cavity chamber that they'll use for megavoltage photons. And using this, it's a very accurate volume, and they can actually figure out what's the real dose in their beam. So if we send them our chamber, they can provide a calibration factor that will go from our chamber reading to the dose in their beam. So I'm kind of stressing that it's their beam because their beam is going to be a different spectrum to what we have clinically. So there's going to be a beam quality dependence. We don't have these on site because it ends up being just too much effort. So we send it to ARPANSA, they calibrate it. And we have a calibration factor which gives us dose to water in a cobalt-60 beam, which is the reference beam that they have under reference conditions. And this is the basic equation that you'll see for this. So when I talk about chamber reading, it's really a corrected reading for influence quantities, but we'll get to that in a bit later. So cobalt-60 is the same everywhere, so that's why it's kind of used as a reference beam quality. But since we're interested in our beam quality, basically the beam spectrum, we need to find NdWQ, not Q0, if that makes sense. So this is our beam. This is the reference cobalt-60. So what that means is that we need to find some correction factor, KQ, Q0, which will give us this NdW that we want. So this will correct for the beam quality. So you can look it up, and so I suppose the best way to put this, we need to quantify our beam quality, so we use this TPR 2010 for photons, which is a ratio, I'll come back to this slide, it's a ratio of the dose at 10 centimeters deep to 20 centimeters deep for a constant source to chamber distance, usually 100 centimeters. And this TPR 2010 is like a surrogate for our beam quality, so we can use it to look up our correction factor KQ. And it will depend on your chamber type and, of course, your beam quality. So our dose to water under reference conditions is our reading corrected times our calibration factor times our beam quality correction. So this corrected reading, what I was talking about, it's actually influenced by so-called influence quantities. So for example, if I measure a dose today and then I measure sort of a similar dose tomorrow, but the temperature's different, you'll get a different reading. So we want to correct for this kind of influence. Temperature and pressure is fairly straightforward. You remember from your ideal gas law, basically, if you've got a low temperature or a high pressure, you have more particles, so your signal will go up. And the inverse is also true. The second one, Ks, that's ion recombination. And this is to do with the magnitude of the voltage you're applying to your chamber. For a lower voltage, you expect that as your charges migrate to the electrode, you can expect two different charges to kind of combine together, a positive and a negative, and then you've kind of missed out on measuring that, so that'll lower your signal. Ideally, you'd want to measure all of them, so I won't get too much into that, but this is your ion recombination correction. So you measure one reading at a high voltage and one at a lower voltage, and the formalism that I mentioned, TRS-398, basically gives us these coefficients so that we can figure out what our correction is going to be, so in kind of a general way, when you measure under certain reference conditions. And we've got a similar thing for the polarity, so interestingly, if you apply minus 250 volts or positive 250 volts to your chamber, the reading will slightly differ. So the way I think of this is that you're kind of normalizing your reading to the average of what you get at the positive and the negative. So it's kind of positive and negative divided by 2, that's the average, and you're kind of correcting to this M is what you're actually measuring at your routine voltage. So hope that made sense. So what we do in practice, we send our chamber and our electrometer. At Charlie's, we kind of treat them as a pair. So we always use the same chamber with the same electrometer. It doesn't have to be the case, but simplifies things a bit. We send that to ARPANSA. They give us back a calibration certificate. So, and then here's the calibration factor. So milligrays per nanocoulombs. So we measure coulombs, we get back in milligrays at the reference conditions. What they also provide, so I'm complicating things a bit here, sorry, but it's TRS-398, the formalism, provides this curve here, which goes from TPR 2010 to our KQ. ARPANSA have actually not just measured cobalt-60, they've measured a few different beam qualities, and they've actually figured out what the beam quality correction factor for your chamber is. So how does your chamber depend on the beam quality for their different beams? And they've provided a quadratic fit which will allow us to just plug in our TPR 2010 value that we've measured and get the corresponding KQ using, they even give us the quadratic equation for it. Okay, so we want to measure dose under reference conditions. Here's our reading. Say it's 1.26 nanocoulombs. We measure our temperature and our pressure. We get KTP. We've already measured Ks and Kpol using this equations. We've gotten our NDW Q0, the calibration factor, from ARPANSA. And we've also taken our KQ from ARPANSA from the graph on the previous slide. So we can finally calculate what's the actual dose to this point. Here's one more. So here's an Excel sheet that we've actually used that I've created. So measuring our TPR 2010, so there's our SSDs and our depth. It's TPR 2010 is just the ratio at these two setups. So 20 centimeters deep, 10 centimeters deep. Here's our ratio, and we use that with our equation to get our KQ from ARPANSA. We could have just used TRS 398 table, but this is a bit more accurate. All right. Here's our raw reading, 250 volts. This is for 3 different energies, but let's just say for 6 MV. Our raw reading, which is actually the average of 3, is 32.28. Here's our KTP, so we measure the temperature and pressure. KS, so we've got 250 volts and 50 volts, which we plug in to account for recombination. And these coefficients come from TRS 398. Polarity, plus and minus 250 volts to get our Kpol. This again is from ARPANSA, and this is from the previous slide. Yep. Finally, what we do here is we measure at 10 deep, but our MU is defined, so our beam is calibrated in terms of how much dose do you get at D max. So at Charlie's, we might say we prescribe 200 MUs to a patient or something. So 1 MU, what we mean by that is a centigrade at Dmax. So there's a little correction here for the fact that we define our MUs here at Dmax, but we're measuring down here, so we just kind of go up the TMR curve. Hopefully you've seen these TMR curves before. Cross-calibration, we don't have time to get too much into it, but basically we don't want to use our special reference chamber that we sent to ARPANSA. We want to use our field chambers, so in case something goes wrong, something breaks, we've still got the one that we actually calibrated and the important one. So read TRS 398. Electrons, again, I wish I could go into more detail here, but the idea is that we're using this chamber is much better for dosimetry and electron beams. We can use our ion chamber, but TRS 398 recommends use the parallel plate chamber for electron beams. And especially at beam qualities above around 10 MeV, it's required. So the point that you're measuring at is here, inner surface of the entrance window at the center. Why is it useful? It's because this measuring, you kind of see this is actually the ion chamber, this is the air cavity, and it's very thin in the beam direction. So you get a really good resolution in this direction. You're kind of sampling a small area. So it's good if you're in a steep gradient, and if you know much about electron beams, you've got a very steep depth dose curve. So if you want to kind of measure a steep gradient, you want something like the parallel plate chamber. And it's a chamber, ion chamber, and it's kind of reliable and doesn't change much over time. So again, it's cross-calibration, which I can't get into, but we want to derive a calibration factor for our rus using our reference ion chamber. So the setup, SSD 100, which is a bit different to photons. We're not keeping the chamber at a constant distance from the source. We're keeping the surface of the water at a constant 100 centimeter distance. And we're prescribing the dose, again at Dmax actually. So. But we're not using TPR 2010 to describe our beam quality. We're instead using this other quantity, R50. And that's just the PDD 50%, what's the depth? So that's all it is. It's like something like, 1.5 centimeters. So, you want to be careful because when you're using an ion chamber, I might be going a bit too in detail here, but what you're measuring is percentage depth ionization, not the percentage depth dose. This is basically to do with how do you convert your charge to your dose again. You need to use the stopping power ratio from water to air. And this changes for electron energies, it changes with depth because your energy is changing. Because your electrons are slowing down, you're losing energy. Whereas for photons, you're kind of just losing the number of photons, but the energy doesn't really change with depth, so you don't have this problem. At the end of the day, if you're measuring your PDD with a ion chamber, TRS 398 provides this handy equation, and you can get your R50 from your ionization R50. So say we measure the PDI, this blue curve, we measure this value here, we just use this equation. It should give you the true PDD value. So that's just to do with Bragg-Ray theory, actually. A few more things for electron reference dosimetry. So your field size, you've got a minimum field size, but you can actually go above that. And the reason is, as your field size gets bigger and bigger, your electrons have a limited range. So if you get a really big field size, your electrons just don't have the range to influence what's happening in the middle. And when you're doing dosimetry, you have a reference depth as well. I didn't really talk much about for photons, but for photons, it's 10 centimeters deep. For electrons, it's this funny quantity, ZREF. So even though our beam is calibrated at the Dmax, we've got this ZREF, which is based on your beam quality, R50. So this is where you want to basically place your reference point. That's where you want to measure dose. And it has to do with, if you use this and you don't use Dmax, you just get a more reliable result. I won't go into too much detail. It's to do with the Linac to Linac beam spectrum variation. But yeah. This ZREF and this Dmax is about the same if you're at low energies. If you get to 18 MV, it's a bit deeper. So. If any of you have been along for a monthly QA session, you've probably noticed we don't actually use water. We use this solid water. So we use the water annually, but it just takes too much time to set up. Solid water is nice and convenient, but we've got our own little correction factors to figure out what would we have gotten in solid water from this reading. So just to go between the two. You might see something different at Genesis or Icon or something. It's department specific, but here we call it PCF, phantom correction factor, and that takes us from 10 centimeters deep to Dmax in water. So you kind of got two corrections. You've got the material to water, and you've got the TMR from 10 centimeters deep up to your Dmax, where its MU is calibrated. So, feel free to have a chat with me anytime if any of that didn't make sense, so if I didn't cover too much ground there. But so we've got, I'll just go quickly over relative dosimetry, different detectors. Diodes you'll see a lot because you're measuring at a very small point and you're getting a high signal. So these are made of silicon, and the thing about silicon is it's more dense than water, so you're going to get more ionization in your little thing. Ion chambers rely on a volume of air, which is much less dense, so you get less signal. And you see a lot of different kinds, for example. So this is what it looks like under an X-ray. This is a stereo diode, and these are a few different other kinds. We'll get a bit more into that. So they are dependent on energy, they're dependent on dose rate, temperature, and accumulated dose. So we don't actually want to use them for our reference dosimetry to calibrate our beams, but they are useful for measuring like profiles or PDDs. they over-respond to low-energy photons in particular because they're made of silicon, which is more dense than water, higher effective atomic number, which means that you've got more photoelectric effect. And then the photoelectric effect is very dependent on your energy. So at the end of the day, diodes have an energy dependence. So for this reason, you've got tiny little shielding on your silicon diodes to attenuate the low-energy photons, to make them a bit less energy dependent. Whereas for electrons, we don't actually have the shielding because there's far fewer of these low-energy photons in your electron beams. There's also this other kind of diode, which you might use for really small fields, called stereotactic diodes. And for these diodes, they're kind of just an extra special case. You don't use shielding because you're in a very small field, and most of the low-energy scatter photons just scatter away. You don't have that equilibrium, so your dose is mainly from that primary radiation, so the shielding isn't really necessary. But you wouldn't want to use a stereo diode for like a 40 by 40 big field, for example. It's just for small fields. Yep. Yeah, let's keep going. You can also use small ion chambers. So this is one that you might encounter. This is what we've used for reference dosimetry, but you can see this is a bit smaller and this is smaller still. The trade-off is less signal, more noise, but you'll get a really good kind of resolution. And parallel plate chambers, I mentioned before, good for the PDDs, or PDIs technically, due to the thin window. And final kind of detector, so we measure profiles in a water tank, so you'll often see this kind of extra detector coming up here, and it looks like this. And we kind of divide the signal here by the signal here, because if the beam output suddenly goes up, it kind of varies over time. If your beam output goes up, then you account for it because you're measuring it here. So it's kind of accounting for variations. Hope that made sense. And that's all I have today. So I hope that was useful. Ask me any questions if you'd like.